So now we have Tim talking about the data analysis for the monochromatic differential.
I'm gonna, like, last night, partly because I hadn't done this in a long time, so I wanted to remember how to do it.
Even if you last night at 9 or maybe 10 minutes.
Yeah, I analyzed, but that's so you can do it, you know, in a few hours. If this is a very like straightforward kind of easy example of it, it can be much more difficult, but I think it'll provide a good example. So I don't think you can see this, but it's like this.
MGO diffraction, very simple, the simplest.
So MGO is cubic. So it's so initially when you put your so here's an example of a diffraction pattern of MGO. So you can see we have a bunch of randomly oriented grains, and each grain is going to diffract out a dot, but that angle is going to be preserved. So depending on the orientation of the grain, it's going to diffract the X-rays at the same angle, but it could be the azimuthal angle could change. So it's going to make a dot on this circle, but since we have a lot of grains, they basically fill up the whole circle. So this is taken before we pressurize or anything. So if we look at our cake plot, our line should be straight, nice and straight, but I'm sort of skipping ahead. Actually, that's the graphite, I think. Graphite or boron nitride. But
So those are not pure sample, right? Graphite, boron, nitride.
It's within, because the diffractive beam goes through the entire volume of the cell. We diffract everything that's in there. So we have the boron nitride sleeve and the furnace, but we want to, before we start, we want to calibrate where, like, the distance of the detector away from the sample, because you can think you make like a diffracting cone, where it shows up on the detector is going to depend on how far away the detector is, because imagine you went up like this, your detector was here, it'd be here, but if it went up like this further back, it'd be up here. So we want to calibrate where like what the distance of the detector is. So this program here is called Dioptus. Here's our image. So to do that,
now you see all the dots.
yeah,
So the grain size is a little bit big.
yeah. So you can see these rings aren't completely filled in because we're just not getting quite enough grains. But I won't go through the entire process. But basically, you put in. We have to calculate the distance. We also have to find out where the beam center is, because they're going to be circles around the beam, not necessarily at the center of the detector or anything. So when we do that cake pattern, when we unwrap it, if we're not unwrapping it about the right central region, it'll look all warped and stuff. So when you do your calibration, you put in the pixel width that we will give to you. The distance, you don't have to put anything. You just click this box, and that means calculate it. You put in the wavelength, the polarization, what you're using as a calibrant. In this case, it would be AL203 alpha. And then I don't like the automatic peak search. Basically, it should just try to find the peak for me. So if I click on it. Yeah, so it found this peak, but I find it kind of doesn't work as well as just doing it automatically. So I do a single peak search. I don't do an automatic increase. And then you go around and you just pick points on this thing. That one was bad, but whatever. And then you go to your next ring and you pick some points on that. And then maybe do another ring or two more or whatever, and then eventually you give up and hit calibrate, which is over here, and then it'll come up with a calibration. I already did the full process, and this has a calibration in it, but we would have to do that, and we'll actually go through that when we run our experiment. So you do this before you pressurize anything. You make sure that you have a nice calibration. And what you do when you calibrate, you go to the cake pattern. I don't know why it's not showing it should show the AL203 here, I would think, but it's not. But anyways, you want to check that these lines are perfectly straight. If they're not, it means.
Just load another file.
I loaded, no, number 2 is, and I loaded it, but it showed up in the image, but it didn't show up in the cake. But anyways, if I hit calibrate, it would automatically go to the cake and show the lines, and you'll have to just believe me that they were straight.
So after dinner, when we load the cell, we'll do that.
Yeah, and then you look at the pattern. Again, it's showing the MGO pattern, but if you look at, yeah, here's the alumina pattern. So if I add the alumina lines, you can see these ones, I think were just like you can see that the lines are straight. So we got our beam center correct. They look a little off, but I actually changed the distance to match MGO because that's what I care more about. So if you look at my MGO lines are nice and in the center. So we have a good calibration so we can sort of do our experiment.
The reason you pick the MGO is that's your pressure standard. So later on, you want to use the cell parameters to get pressure. So you want these peaks to be exact, at the same position as the reference file tells you.
I think it's like 460. It's usually around that. Yeah, 460 millimeters away. So it's usually around that, like a little less than half a meter away. You can vary that. Sometimes you want to move the detector back, or you can move the press forward so that the detector is further away, because you can change the energy and that'll change the angle at which it diffracts. But sometimes you need to go to higher energy because you have an absorbing material. So you'll want to go up to higher energy and move the detector away to increase resolution. Does that make sense? Okay. So now, if I go back to this, we're gonna get our cake patterns out. So I'll just pick somewhere down the line where we have a bit of stress built up. I think there should be some here. So now you can see this is after we pressurize and we're deforming it. This was just done at room temperature. So you see that the peak has shifted now. We can increase the pressure. So we're at about a GPA and a half. The people, I think I brought this up. Are people familiar with the Birch-Moynihan equation of state? Put up your hand if you are. So one EM. So basically, it's this equation here. So you get pressure from the volume of the unit cell of what you're looking at. So usually you'll know what the volume of the unit cell is at zero pressure, or you could measure it because you're measuring it with the diffraction peaks. And then, so basically from the diffraction peaks, you can get the cell parameters like A, B, and C, because you know how far away the D-spacings are. And then from that, you can get the volume of the unit cell. And when you compare the volume that you measure at some higher pressure compared to a reference, usually ambient pressure, and you plug that into this equation, you can find out what the pressure is. Do people sort of understand work? So we measure from the...
Don't know. So Ken was talking about the bulk modulus and the pressure derivative of the bulk modulus for elasticity. And for the pressure standard, let's say MGO, these parameters are known. So you know the bulk modulus, you know the pressure derivative of bulk. So if this equation, you can use by plugging in your volume at certain pressure. You don't know the pressure, but there's some pressure. And you take the ratio of the room pressure volume and your measured volume at unknown pressure, you plug into this equation, you can calculate the pressure. This is what we call the equation of state. This is only at room temperature, but there's a high temperature equation of states equivalent. You can calculate your pressure at any pressure and temperature.
Right. So in this case, we didn't increase the temperature, so it's not a factor. But you see how, so this like PGPA, when I'm increasing this number in the JCPDS file that Pam talked about, it has the bulk modulus and its derivative, and then it just runs through that equation. So it's using the Birch-Moynihan second order equation of state to show where the peaks would be, like where the peak would be at, in this case, 2.5 GPa. For temperature, you'll notice as I increase the temperature, the peak goes the other way. So what's happening is as you pressurize it, the D spacings get closer together because it's getting smaller, which leads to wider angles of diffraction. But when you heat it up, then the D spacings want to expand. So what we typically do to get the equation of state is we have this Birch-Moynihan thing. Good. Oh, it's over here. We use this Birch-Moynihan equation of state. And this is not the only way to do this by any means, but we'll put in our volume and we'll find out what would be the pressure if it was at room temperature. And you'll get something that's lower if it's at high temperature because high temperature is making it expand. But when we add the component of temperature and say, if it was just at high temperature, what would the pressure be? Because you get thermal pressure. So it's like you add the component from the pressure and the component from the temperature.
This is why the JCPDS files have this thermal expansion term in it. So
because of the crosstalk between those two parameters, you need to know one. Otherwise, you can put any combination in there, it'll fit.
Right.
but it's not really precise. So basically, the first approximation is you take the product of thermal expansion and bulk modulus. That's approximately the thermal pressure for a given temperature. So you calculate alpha at certain T, the K at times the bulk modulus times that alpha times the delta T, that gives you the thermal pressure. Approximately.
The question is, the bulk model is also a function of temperature.
Yes.
It is.
Yes.
That's why you're doing it this way, where you're referencing everything to ambient conditions.
Yeah.
So this equation here takes in the bulk modulus and its derivative at ambient conditions. And then you use the thermal expansion to get the temperature, and you take that value at ambient conditions. So it would be like, what you're sort of saying is that, let's say you have, let's say this is pressure, this is temperature. Then you're saying you have like a certain volume, and you'll say, what would that volume, based on the D spacing that you have, right? You're measuring the volume, you're measuring the D spacing, and you're saying like, what pressure would this D spacing correspond to? And you'll come out here at room temperature, but then you'll say, what pressure would what volume would that, so it's like you're adding a component of room temperature or of pressure at room temperature, and then adding a component of temperature at ambient pressure. I think I did a pretty bad job of explaining that. Any questions? Do people feel like they kind of
I think he touched on that. So the bulk modulator itself is a function of pressure and temperature. Thermal expansion is also a function of both pressure and temperature. So as you increase the pressure, thermal expansion goes down. Okay. As you increase the pressure, the bulk modulus goes up. And there's tons of studies since the 1940s and 50s. People compile all this ceramic data, and most of the data would say that alpha K, the thermal expansion times the bulk modulus, pretty much remains constant, because the opposite effects cancel out most of the errors. So for the first approximation, you basically just use alpha K at ambient pressure and temperature to estimate the thermal pressure. And you do the correction. But it's important for you to keep that in mind. This is not precise enough. So after you collect the data, when you go home, analyze data more precise. There are a lot of different software you can do to get precise pressure measurements.
For the software that you're using, are you primarily using it as you're collecting the data, or to simulate possible scenarios of the experiment you are doing to get probable outputs?
I'm not sure if I fully know what you mean, but usually we're doing it like with reference to the peaks that we have in our experiment.
Okay.
So
Collect the data.
yeah, we're not trying to like go up to this place. Well, maybe we are. Like you could kind of move it to, if you wanted to run your experiment at 5 GPA, then you'd wait until the peak reaches 5 GPA.
Okay.
Kind of thing.
Well, I was just wondering, because since you can kind of change the variables to show like where your peaks would end up under different situations,
Mhm.
I wasn't sure if you use that ability just to see if things would change under different pressures or temperatures, and if what you were actually doing reflected that in your true data results.
So I do that a lot before an experiment to see if materials are going to overlap each other, or it's going to be difficult to resolve diffraction peaks from different materials in the beam path.
Okay.
So where you can take like JCPDS standards and you can play around with the pressure and play around with the temperature and see, well, I want to do this at 5 GPA and 1,000 degrees, but crap, they're right on top of each other. So we're going to need to change the conditions of that. And it helps you kind of guide where you want the experiment to go. And you can use it like if you want to target pressure, like you said, just go and collect diffraction during compression until your peaks line up with the place that you want to go. Dioptust is really, really good for an on-the-fly during the experiment measurement and comparison tool to be able to get you where you want to go. It's not going to be the end-all, be-all and the theoretical model that you're going to use to
Dioptust isn't. Sorry. Dioptust isn't really for analysis so much. It's just a really nice GUI to like cycle through images. So I'm like skipping, this is moving forward in time. And it doesn't look like the stress is increasing all that much. There's something happening, but you can see texture building up.
It's a very good display software. And what's really the other useful aspect is if you have a low symmetry sample you want to study, you want to know which peak you're going to focus on. For example, there's a lot of peak overlap. There may be only one peak that's not overlapping. You want to focus on that one. So you can use this to say, okay, if I apply pressure to 5 GPA, will this peak move out of my range? So then I need to select a different energy, photon energy, to make it move it into the range so I can collect the right data. So it's very useful for this.
Can you also manipulate the energy output for those peaks within it? Like outside of
this, where you give an energy where the peak should be. If the peak is not at the right place I want, then I change the energy. Then I can estimate where I change the energy, and then I look at it again.
Yeah, in that calibration screen, you can give it a different energy and click update calibration, and it will shift the peaks to where that would be under that different energy. So you can model what you're.
That's really
good. But so we know the energy.
Mhm.
because we like decide on what we want to use with the monochrometer.
Right.
So that's like an input. In theory, if you knew everything except the energy, then you could use it to find out what the energy is.
Right.
But okay, so this is sort of towards the end of the experiment. So we built up more stress, but you also notice something else that you see how it's brighter at these points. So remember from our image, the like where it ends up around this ring has to do with the orientation of the grains. So during the experiment, if you look at something near the beginning of deformation, okay, there is a little more photons like at 90 and 180 degrees, but not much. But if we go to the end of the experiment, and we look at it again, one, we have a lot more stress, and then two, we have brighter places around the ring than others. So since the orientation of the grain determines where on the ring it will diffract out to, this is saying that we've rotated grains and aligned them such that a lot of them, or many of them, many more of them than when we began, are pointed in a particular direction. So they're diffracting to that angle.
Could you also just have big grain there, or would that look different?
If you had a big grain, it would be a really bright, but just a single spot. I guess it's possible that you had just like a large grain came into your thing, but then it wouldn't be symmetric either. You'd only have it at one place, not on the other side. That seems kind of unlikely though, that out of nowhere, like you don't measure it before, and then at some point you just have a big grain come in. And what happened to all the other, diffracting grains?
These things have symmetry.
Yeah.
If you look at this, if you imagine you connect this one to that, that's exactly the same intensity as this. So it's kind of a symmetric thing. If you have four different single grains that happens to be at that spot, that the chances are very slim.
Yeah.
Is vertical 90 or 0?
Vertical is the maximum compressive.
Right, but the azimuth.
The azimuth in this is like 90. This is 90, and this is the maximum.
So that's 90.
0,
Okay. Because if you go back to the first one that you had before you did any of the deformation.
So this is pressurized but not deformed.
So
Cake it.
it's forward scatter from the beam that gets in between the anvils that come through. So everything along that path is going to be brighter.
Oh yeah, that's true.
That's an overprint on it.
That's a good point.
That's the same thing that we have, and except ours is slanted at that 54 degree.
Yeah.
To do it quantitatively, you want to take the diffraction as a reference and remove the background.
Right.
Yeah, that's a good point. So you already have brighter stuff at the top and the bottom, because you're coming through an amble gap on the one side, and there's an amble gap on the back.
Yeah.
And then there's transparent diamonds. So if you look at the image, like along this line is things that are diffracting through the amble gap.
Yeah.
But around here, they have to go through the diamonds, so they're going to be somewhat attenuated.
If you look at here and here,
Yeah.
that is the shadow back.
Yeah. There may also be a little bit of texture developed during pressure, but either way.
Diamonds are great filters.
Yeah. Thanks, man. That's a good point. So now, like, what we want to do, we've talked about this many times so far, is we have our right? Say we had a circle when we weren't under stress, because all the grains, or we could be under hydrostatic stress. And we'll get a circle. It means all the grains are compressed the same amount. But when we start to compress it, or when we start to deform it, so like add extra stress from the top and the bottom, now the grains that are going to diffract in this direction, so let's say those are these ones, they're going to be closer together than ones that are this way, because we're pressing harder onto this lattice plane. So then we get an ellipse. And then what we want to do is we want to fit this ellipse. So like the ones in here are intermediate. They're not perfectly aligned with the maximum compressive destruction, but they're not 90 degrees to either. And what we want to do is we want to fit this ellipse, and that will tell us what the differential stress is in our experiment. And the way we do that is if you look at like this thing here, this 1D pattern is just adding up, integrating around the ring, and then so using that as a 1D thing. If you look at it though, like, so if you look at the intensity profile across this, it's going to be a peak. And what we do is we just take, you know, let's say like a 5 degrees, and we'll integrate that. And then the next 5 degrees, we'll integrate that. Then the next 5 degrees, and we'll fit all of these different peaks around the annulus. And then once we have the D-spacing from fitting all of these different peaks, so we can just look at the D-spacing of these peaks. 2 theta and D-spacing are proportional or inversely proportional to one another. So we're going to fit like a peak across all these things, and they're going to make this profile. So then when we fit all our peaks around this circle, we get a profile that looks like that, and then we fit this profile. And from there, we can actually get what the differential stress is. Did that make sense to people? And the equation that we use is this one here. So this is strain, but it's lattice strain, not to be confused with the macroscopic strain of like the sample changing shape. But you'll have a term that's related to the like pressure strain, like the hydrostatic term, and Pam talked about this. And then you'll also have, often this is written as Q, you'll have this term which relates to the differential stress. So when cos squared theta equals 1/3, then you'll have one, I don't know if you guys can see this, but you'll have 1 minus 3 over 1/3. This will be 0 if you don't have any differential strain. And you'll just be left with the pressure. And the angle that happens is at, I think, around 54 degrees. So if you want to know what like just the pressure is, you'll have to look at what the D-spacing is at whatever 54 degrees, somewhere where it is. So now we want to export our data. This is not a great way to export the data. It's very time consuming and kind of, I don't know, it's not great. But basically you go into the cake pattern and then you save it. And you want to save it as a text file. And this will all become apparent after. I'm going to put these in. So I've saved my cake pattern. Then I go to the next one. And I do it again. And I'll do 3.
We need to make the batch function.
Yeah. So there is a way, if you have 25 patterns, it's annoying, but it'll take you 5 minutes. If you have like 1,500 patterns, you really wouldn't want to do this. And I know a way that you can batch process them, but that is also kind of a really annoying program. I will say though, this, like the guy who wrote this program, he used to work here and he's always upgrading it. So I suspect in not too long, there'll be a batch process to it. But at the moment, there's not. So I'm just going to do a few for now. I'm just going to do, because I did all this analysis yesterday. So I can show you like what the results are. I even did this one already. Okay, so I'll just do those 3 for the analysis for now. So the program that we use is this program called Multifit. And you want Multifit Master. That's like the newest version. All of this software is free. Multifit Master and this other program, PolyDefects, they run in IDL, but you don't need IDL to run them. You can get the IDL virtual machine, which is like a
You already have the
lesser
machine from the magical.
Oh, okay. It's you have it already, and it's basically like a lesser version of IDL, but it can run these things, and it's free. And so is this software. Were you gonna say something?
It's the one stick.
Oh yeah.
The software was produced by Sebastian Merkel in France. And he has a paper describing all the details. If you're interested, I can send the paper to you.
Yeah. So we want multifit.save. This is the like executable thing. So here we want to, you need to put in some parameters. So we need to put in the wavelength and the sample detector distance. So we can get that from Dioptis. So the wavelength is 0.2431 angstroms. The sample detector distance is 459.9. And now we can put the directory, their files in it. So okay, so and we'll just save everything in the same. So now we're gonna import the data, and it's gonna take those text files that we just exported from Dioptis and turn them into IDL files. So file, yeah, Dioptis, TXT files, and then select all of them, open, and now I think it should bring them in. Is it working? Looks like no. Okay, so now it's saying that the current number of azimuths from basically minus 180 to plus 180 is 1,000. So that's saying it's like around the ring, it's taking 1,000 little slices. So imagine you took 4 around the ring. Then you just have like, this would be 1, and then you'd integrate over that to get a single 1D pattern. Right now, the default is 1,000. That's a lot. So I'm going to divide by, it was 14, gives me roughly 5 degrees. that I'm gonna integrate over. So I'll have like 72 points around the ring. And I'll say, okay. So now it's gonna do that like integration for me and make my IDL files. Okay, yeah, there's one. Two. Okay, this should be done now. Oh yeah, so there's my files. So now I want to fit my peaks. So if I go to peak fitting, so I'm just going to choose this file, number 145. And then I fit active data set. And now I'm going to fit, this is just like choosing which azimuthal angles I want to fit. In this case, I'm going to fit them all, but sometimes you might have a gap. Like if you don't have, if your whole ring's not completely filled up and you have a gap, you're going to deselect that particular angle because there's nothing there to fit. Or if there's just something weird around it or whatever the case may be, you may not want to fit every single point around it. Pseudo void peaks. I don't really know what this stuff does. I've messed around with it. It can change things. If you figure it out, let me know. But
Well, there is the weak peaks where you want to actually emphasize it, and you know how many steps you want to do.
yeah, there's different. It's basically in this case, it won't really matter because the peaks are strong enough and they're fine. But like, do you want to do the number of loops? Like, how many iterations do you want to go in to find it, and so on and so forth. But anyway, I'm just going to leave it whatever the default is, and I'm going to say fit. And then this peak was graphite, and this was our first MGO peak. So you click on the left and right side of it, and then we do it again. And then we can fit, it says here, like the maximum, it says left or right side. Do they mean like a half width or at the bottom? It used to be click on the half width. I went towards the bottom, sort of like here. I don't know if that matters, but anyway, you'll click it.
You where where it's considered a peak.
Mm-hmm. Yeah. You're trying to like enter in, you know, where does the peak turn over? What's its maximum things? But that was it's kind of weird the way it's written. But anyway, so here's that's my fit.
French.
Yeah. So the data's in black, I think, and then my fit's in yellow, and the residuals are down here. So I'll take this. And now it's just going around using that initial fit as an example. It goes around the ring and fits the rest of them. And doesn't look like it's doing the best job in the world.
Well, this is a weak peak, right?
Yeah.
The very first one, it tends to be very weak.
But
you can see
so it doesn't have, the data quality is not good, but you can see that it did at least end up with that like cake looking pattern. So this is azimuth versus 2 theta. So it's good enough for this demonstration. So save results in a file. I'm going to do that. So you need to know what peak it was. So like what the HKL was. So it was this peak here. So I can just go back to the beginning. Yeah. And then you can look in, if you actually have this, you might not. So if I go to edit for my JCPDS file, it will give me all the different HKLs and their despacings and stuff. So you can look at it in Dioptus that this one is at a despacing for 0 of 2.437 and 2.432. So I know it's 111, but you'll need to know, like, accurately say which peaks are which. So take the results in my here and I'll call it I usually put down that it was like image 100 that or no, 145 was the one I took it from, and it's HKL. So it's saving like my initial conditions to fit the other peaks automatically. My initial choices that I had there, it's saving that like model kind of thing. So we can save it. For some reason, it asks you for a title for the file. Yes, that's just the name of the file, which I just named. I don't know, but I always just put the same thing. And now, so you need to fit, to get the pressure, you need to fit at least as many peaks as there are degrees of freedom in your like crystal symmetry. So cubic is the angle between the things is 90 degrees. So that's like set. We already know that. And the length is the same on all three sides. So you only need one. But if you had a triclinic crystal where you have A, B, and C are all different and the angles between them are all different, then you need to fit 6 peaks. So as long as it's, you know, you just need more than the number. But since there's 3 strong peaks here, we'll fit 3 of them. So we can fit the next one, which is this one. This is 200, right?
Yeah, this is the strongest peak. You can see, that the statistics much better. The peak shape is also there.
So
They got 3 panels. The bottom one doesn't show anything. I don't know why. The very top one is the 2 theta variation. Second is the intensity variation. So later on, the intensity variation can be used for fitting the texture.
yeah, I don't know.
So
Gaussian sigma?
Gaussian, yeah.
I don't know what that.
There it is. Now it showed up.
Oh. Okay. Okay, so we got one more peak to fit. I think this is 222.
220.
220. Oh yeah. Just
symmetry. Yeah, so you have to pick a void or pseudo void in this kind of fit because the sample is under stress. So you don't have an equal distribution about different orientation grains inside. The grains are skewed to the right hand side, so you see kind of like tail-like thing. So
okay, that looks weird. This looks kind of like the beam center is off because it should be symmetric about that. You can correct for that in the later program. So I'll save this in a file.
But it's a possibility because as you heat the sample up, the Hodge temperature goes up. You know, everything we have in there is at least 1.5 meter tall. And 1 degree temperature fluctuation would make the whole thing drift out slightly, and then your center will be off.
This was at room temperature, but
This is room temperature.
Don't matter. So anyway, so now we have our peaks and we want to like batch process the stuff. so we made our. So we want to create a fit model. So we'll use pseudo void again, and we'll add our 3 peaks. And we'll create our model. Now we can fit multiple images based on that model. So let's just fit the first 2. We'll enter our model. And then save our fits. And so the level of plots, this is going to show the plot of each fit. So if you do verbose, it's very slow and shows you a lot of information. No plot is much faster for the computer to run. I'll just do for now 1D minimal, but if everything is working really well, you may not even need to look at the data being fit. But if it's not working well, you might have to slow down and watch it and fiddle with parameters and things. Yeah, and this is just saying like how wide is the region that I'm fitting in. For this, it doesn't matter because the peaks are really far away, but if they were going to overlap, you wouldn't want to use a really big region because it might fit another peak. Another reason I'm saying. Oh, but also if the pressure and stress change in the peak moves a lot, you'll have to have a bigger region so that it'll, check in that area to find it. But I think this should be fine. So now it's fitting our peaks for us.
So this is fitting the next data file,
Yeah.
the second data file. All 3 peaks automatically.
So now we just switch to the next peak. So this is the 200, the big one. I think this was the 3rd, yeah. Yeah, and it says in here, like. And now it's doing the next diffraction image. So it was the 3 peaks in the first image and then 3 more peaks in the next one. And then once this is done, I'll fit the other one, but I won't use the like plotting out. We'll see how fast it goes. Yeah, so it's way faster. So now we fit our 3 peaks and we want to look at like how we did and what's the stress and strain and all that. And I will, I'll just show, I think there was like 100 images and I already did that. So I fit them all yesterday, the same process that we did, but for every image. And then this other program called PolyDefX, and make sure you get the master version. That's what we're using. So first you use multi-fit to do the peak fitting, and then you use PolyDefX to look at the results. There's another program called MAUD, which I've never really used, but it also does this same sort of analysis. So there's a bunch of things that we have to set up first. So set fit files, so our fits, like it's saved. So it saved the fits in the directory here. And we have to tell it, you know, which files to import. So that's just saying the root name is D2409_D. We're going from 100 to 204, and there's 3 digits. So it just imported them or found them basically. And then the material properties. So here's where you put in material properties about MGO. So the symmetry, the cell volume at ambient, the bulk modulus, and the derivative. Now that stuff, you'll look it up in like a paper or something. Somebody has measured this. So we're going to use anisotropic for our elastic model. And when we look at the options, we have to put in these elastic constants like our CIJs. So in this case, because it's got high symmetry, it only has 3 CIJs, but depending on the symmetry, it could be much different. So like if I change symmetry, let me just remember these. So what is, I guess this is for if you're fitting like a.
It's a pressure derivative and the temperature derivative.
Okay. Yeah, but I know I just grabbed this. I didn't even look in a paper. I just looked at like AI on Google. But if you were doing this, you know, actually, you'd want to put a little more time into this. So if you have the pressure and temperature derivatives, you could put them in. If you know, if someone has actually measured the CIJ at the particular conditions that you're running it at, you'd want to enter those. Sorry. So if I go to like orthorhombic and look at, there's a lot more CIJs, but we have cubic. We want to select our lattice plane. So 1 just means use it or don't use it. So 1 or 0, and then you put in the HKL. Set the wavelength. We already know that from Dioptus. And our fit options. So our maximum compression direction in our image is 90 degrees. So we put in 90 degrees, and we're going to fit the beam center. So we click yes. What's the other one? Fit offset for compression.
Yeah.
What's that?
I never used that one.
I've never used it either. Yeah. Offset. Oh, I guess if it was changing slightly throughout your experiment, so instead of pointing down, it pointed at 89 degrees and stuff and moved around a bit. I don't know. But anyway.
So you can do, you only have 2 choices. 1 no, 1 yes, or 1 yes, 1 no. You can't do.
Yeah, you can't do them
yes,
both simultaneously.
Because they are not compatible.
Yeah. So we're going to fit our beam center. And now we can look at our data. So, sorry, if we go to stress and strain, if we test the fit quality, so this is going to do a movie through it, and we're going to see how well we like fit our cake. So we can take, this was the one that we had the best data on. We'll correct for the center, and then we'll run our dynamic plot. And then it'll just show like going through. So at the start, we have very little stress. And we're deforming it, so we're building up some stress. You can see that the fit is not great, especially at the high angles, but it's reasonable. And we're building up stress and that's what it looks like.
You want to plot the stress?
Yeah.
Oh, it's still going.
Yeah, so I think there's like 100 images in here. Let's see. So this one was worse data though. Let's just look how it is.
Stress is high. It's still kind of centric.
Yeah. Yeah, it does look like even with the correction, it's still a little. Yeah, I think. Oh, it came back bigger. Sit through it again, but I kind of want to see how it does. Oh well. That's homework assignment. Okay, okay, so let's see what the pressure is. So we see that during our experiment, the actual pressure was increasing, not just the differential stress. Or is this, so is this calculating pressure at like 54 degrees, or is it
Yeah.
taking all three and then taking the average?
It has to be the same. Yeah, pretty much the same. But the CIJs you put in didn't have the pressure derivative, right?
No.
So it doesn't give you the current pressure.
Yeah. The other thing is too, if this is assuming that it's at room temperature, but if it was at high temperature, you'd have to add the component of thermal pressure to this pressure here. So if you saw that, like if you heat it up, it'll look like your pressure dropped a huge amount because it's expanding and the despacings are getting further apart.
Yeah. So strictly speaking, this pressure is not reliable. You gotta analyze your data and use the right equation of state to calculate the pressure.
Yeah.
This only gives you a kind of a guide. Pressure is increasing. Okay, this looks like a quite linear, kind of surprising. Actually.
Yeah. So then the volume is just going to be like the inverse of that, since they're inversely proportional. So the cell volume is getting smaller as the pressure goes up.
Stress.
There's this.
That is strain.
Is it? Can you? I don't think you can do stress. It's just the lattice strains.
It should give you the stress too.
Well, anyway. So here's our three different. The Q value is the like differential lattice strain. I thought it did. That was because we had to put in the. Oh yeah, stresses. Yeah, I was like, last month.
Yeah, this is what Pam says. It will be different.
Yeah.
Yeah.
So you see all three lines gave a slightly different answer for the stress. And it's actually like this one's 2 versus 3.5. So it's quite a big difference. So the people, I only have a very hand wavy answer as why this happens, but do people understand what's going on? Like, why don't you get the same stress for each peak? No.
Did they say it's because different like clusters of grains are contributing to each peak, or was that related to something else?
Not really.
Or orientation.
Maybe orientation, I don't know what you said. They orientate differently. So
Yeah, it's related to the orientation. So like different like an HKL is a different lattice plane. So you'll have this lattice plane, which is like this difference away. But after you see other the same at the beginning, and then they split off. So this is the elastic region. So, but then when they split out is when you start getting into plastic deformation. And plastic deformation is the presence of defects moving through the crystal. But we can only measure lattice planes, like the difference between lattice planes. So if some defect jumps through our lattice planes, we don't pick that up because we're just measuring the difference, the distance between the lattice planes. And depending on what the slip systems are, certain lattice planes will slip more easier than others. So you'll relieve stress through plastic deformation. Does that make sense?
So I think when you get to the stress, you already used one important assumption into it. I think in this calculation, it assumes the stress is Roy's. Yeah. So what we really need to look at is the cube factor. Because when you convert the stress, we had that equation there. That equation assumes Roy's bound. And it actually blows up this difference. And that's only one bound. There are two extremes, right? We have the Roy's bound, we have the void, and also the isostrain bound. We can't do the isostrain bound because grains cannot overlap. So, but when you do the Roy's, you're assuming that every grain in that orientation feels the same stress, which is also not true. And that's why Pam used the self-consistent model to get a better estimate of this thing. But the self-consistent model is also not perfect. Because as Pam explained, you assume an average matrix and you plug one grain into it. And this grain, you don't care the shape, but you assume it's an ellipsoid shape. And then you modify the matrix response because of that grain. And then you plug another grain to it. And in reality, what we see here, the diffraction gives you some signals only from those grains that satisfy the Bragg condition. There may be tons of grains that we don't see here. So it's it's a very complicated issue. And I don't think there's a perfect solution at this point.
Yeah, that's the drawback of the assumption. Assuming that it's an ellipsoid when the only thing that you know for reality is that it is absolutely not an ellipsoid.
Exactly.
So there's all of that comes into play.
And it doesn't take into account of the interactions of the next grains. Yes. You have one grain, you have other grains in there, right? One deforms, all the others have to follow. And in the self-consistent model, that detail that cannot be taken into account. So there's so many issues in there.
Yeah. And if you knew like at each sort of point or within each grain inside the crystal, you actually have a stress distribution. Like this is sort of an average of the whole setup. And you see that there's definitely a large component of stress in the direction that we're pushing harder on, but it's not necessarily the stress that each individual grain feels.
So it gets worse too if you have a material that it is not a single phase, a single material.
Yeah,
because then you're going to have stresses from the different surrounding grains that could be completely different yield strengths, completely different properties from each other. So, the bottom of your quartz crystal might be next to another quartz, but you might be next to a feldspar up here. And the whole thing is completely different when you go from one to the other. And all of the assumptions and all of these calculations have to remove that in order to make the calculation feasible.
Even for a single phase, Pam showed that 10 peaks for olivine. What if you use 5? Mm-hmm. What results you get? If you use 7, what you get? So my guess is if you use different number of peaks, you'll be getting different results. And then the question is, how do you know you have enough sampling to represent the whole thing? Right. So I think the real bottom line at this point is, we can resolve some relative changes in the stress and strain curves. The absolute values may be floating somewhat.
And I
But
think,
the change relatively, you go from 1% strain to 5% strain, you change the stress by certain, increment. That you can really talk about. The really precise, you say, can my MPa stress? We're not there yet.
yeah, the other thing is, I think like what Pam showed, when she had 10 peaks or whatever fit, the average was a reasonable average. But if you look at, in theory, I only have to pick one of these lines to get my pressure and everything because it's cubic, but I could be off by, a GPA and a half if I fit this one versus this one.
And I have another question.
Yeah.
So to determine kind of what is acceptable peaks for a number when you're doing an experiment is repetition and just doing numerous cells to see if you get similar peak results, like kind of how you would tell if the peaks are averaging, or is it
Like,
Not really, because the peaks, whatever the peaks you have, is determined by Bragg's law and the symmetry of your sample. You can
Oh, yeah,
repeat
that's
experiments, you
different.
always get the same peaks. Yeah, you don't get some peaks that they're not supposed to show up
Mhm.
from the crystals. That what peaks you have is
Sometimes you do.
so basically, what's determining the peaks is the symmetry of the material. Once the symmetry is fixed, the composition is fixed, that's the peak you get.
yeah,
Yeah.
so ones with like minerals with the same symmetry, their despacings might be different between different minerals, but the pattern will still be the same if they have the same symmetry.
okay, no matter how the stress temperature,
Yeah.
okay.
Yeah, and that's where if you can't see certain peaks because of the parameters of the experiment, then that's what you were talking about before, where you can change the energy to try to bring the peaks into view because they're just simply not in the Bragg condition to hit the detector. They might be going too wide and they're out here somewhere and you want to change the energy to bring them in. So there are ways to get around it, and that's what comes from multiple repetitions and whatnot. But the nuts and bolts of it, those despacings are particular to a particular material, and that's really what so that I always have a hard time because people like, I'm going to pick on diamond cell people for a second. They always like to report things in 2 theta, like all their plots are 2 theta, and that doesn't mean shit to me, like because 2 theta depends on so many different things. But despacing is reality. So if everybody reports despacing, then it's something that you can look at from one to another and know what you're looking at. So despacing is the holy grail. That's what we're looking for in experiments.
Yeah, that's like the physical reality of it.
Yeah.
So we can also look at the texture. So this is just looking. Oh, sorry. So this is the intensity around the ring. Just pick the big one, but you have, so this is at the 90 degrees. Remember, we had brighter, but it's, as Matt was saying, it's usually going to be brighter here anyway. So this probably isn't to do necessarily so much with texture yet. We haven't developed a lot of texture. This is probably just because it's brighter at the top and bottom because there's a gap.
Looks like
But now we are starting to actually develop texture.
Yeah, that's,
You can also see
that's
that's a clear overprint.
That's very
Yeah,
nice.
that's nice.
And let's look at another.
No, that was probably hopeless.
It wasn't until like later though that we
Yeah, you want to
picked
wait
up-
until 170 something.
Yeah. There's something there, it's
Yeah,
not
there's
that
something.
well resolved, but.
Yeah.
It is, because that should be off angle, right? But it looks like it's almost.
It's different.
Yeah.
Yeah.
From the,
This is all because of what we call the slip systems, right? So once you have the lattice, how do I show all this thing? So, so first the lattice, and you have a defect over here. This dislocation slips easily on certain given planes depending on the density of the atoms in that plane. The higher the density, the easier for the dislocation to propagate. So when the dislocation propagates from here to here, it goes off the grain. You actually, so the whole grain will change to this shape, right? So the lattice will change, the lattice remains the same, but shape changes, right? Because you move matter from this end to the other end. And well, as you do this, because of the neighboring grains, the lattice has to rotate. So therefore, some particular plane will become preferred along certain diffraction vectors. So you see the higher intensity only along certain azimuth angle, depending on the lattice plane that slips around here. So this is the important information. You can use this information to determine active slip systems.
What's the use of the peak widths?
Peak width, it's a measure of how distorted the lattice is. Right? The lattice can be distorted due to a variety of reasons. Probably most likely is the neighboring grains are impinging on this grain. Then you have heterogeneity. So the lattice dimension should be exactly the same, but the stress is not homogeneous from the outside. So there's a local variation, and then your peak will become broader. Or maybe other reason, you may actually produce point defects in the grains, which don't propagate very fast, especially at room temperature.
Okay, I think that's about it for the angular dispersive diffraction analysis. Did everyone feel reasonably comfortable that they could probably do that? I think we have, like, I know you don't remember every step and everything. Inman sent me a manual, I didn't read it. I realized that I knew how to do it like after I sent you the email, but thank you for doing that.
Welcome.
So
I need to actually update the manual, make it work.
Send a copy of us too.
I can send that.
Yeah.
Right now, it's not in a great shape because it's
No,
kind of
but
like
if you-
internet notes.
That's what I was saying. If you send it to me, I can try to help you with some updates. if you
Great.
want.
Okay.
Yeah. And certainly if you run an experiment here, we can help you with the analysis.
Yes.
This was a very straightforward, easy experiment to fit. They're not always anywhere near that easy. Sometimes it can be quite difficult to get everything just right. But yeah. So maybe take a break.
Can I? You mentioned earlier that, and I don't know if this works for Caleb, but Caleb, you just got here, perfect timing. So one of the things that was floated as a suggestion earlier is maybe, would you be able to talk tomorrow after lunch?
Sure.
About that? Because that would be perfect, because then we would be able to see everything and we'll have all that stuff under our belt. There was the theoretical platform that Pamela provided earlier, and then we can cap it up with what you're going to be talking about tomorrow.
Sure.
So tomorrow afternoon. So dinner is
then it will be
dinner's at 5:30. It's an hour until then.
We can go to
If we load the cell now, then we can go home after dinner. I'm just saying.
Yeah.
If we can also open up the DDIA and you can see, because it's down at room pressure, and Grace and Bailey, I think, are taking a nap so they can sleep. Well, they can stay awake all night. So if you would like to see that as well, we can pull that out. Okay, if you want to do that.
Yeah.
I think,
And you can make more of the Smoky quartz.
Smoky quartz.
Oh, yeah. Do you mean like, just so people can see the D-dia where the handles go and stuff? Or?
Pull it out and see the experiment they just did this.
Oh, I see. Yeah, okay,
Yeah.
it's decompressed, so
Yeah,
they can,
yeah, it should be at room pressure now. We could take the whole thing.
Okay, how long does it take?
It'll probably take about 15 minutes to open the press. It's at pressure right now. I mean, you could do something else and then come down there
Yeah,
because
maybe we could do the setup here first.
Here.
And after dinner, we walk over there and you take the cell out and then we call it a day.